This is Silvia Quaresima from the EAES Technology Subcommittee for Fluorescence Guided Surgery. In this video, we are going to talk about the physical basis of fluorescence. In the last years, indocyanine green fluorescence guided surgery has gained progressively popularity, obtaining a large diffusion in clinical practice and minimally invasive surgery. Aim of this video is to describe the physical principle of fluorescence phenomena at the basis of the actually available technologies. The concept of fluorescence was introduced in 1852 by George Gabriel Stokes, who describes minerals with specific properties, fluorite and uranium glass, such as the ability of emitting blue light when irradiated by a light source. Fluorescence is a common phenomenon in nature when energy is absorbed by the fluorochromes, organic molecules, main aromatic ring of DNA, sugar, and proteins. A promotion of the localized electrons from ground state to an higher energy level occur. Upon returning from the exciting single state to ground state, energy is emitted as photons that reach the observer's eyes as fluorescence with a specific wavelength. The amount of the energy is realized as fluorescence is lower as compared to the energy that is required to promote the electron energy gap, because a certain amount of this energy is released as heat. The fluorescent properties of indocyanine green are known since 1955, when the Kodak Research Laboratory studies its physical features for application in photography development. ICG was approved by the Food and Drug Administration for clinical use in 1956. Since these dye have been largely employed in many branches of medicine with different applications, like the measurement of cardiac output, study of retinal vessels anatomy, and evaluation of liver reserve in cirrhosis and in metabolic liver disease. Moreover, ICG is useful in many branches of surgery like cardiothoracic surgery, neurosurgery, digestive, plastic, and oncological surgery. In fact, when ICG is administered intravenously, it binds to plasmatic lipoproteins and undergoes rapid vascular distribution and subsequent biliary concentration and secretion. Instead, if an ICG solution is administered subcutaneously, the molecule is able to map the lymphatic drainage. Although the properties of its and clinical application of ICG are known since the 60s, it was only with the more recent development of dedicated laparoscopic probe that ICG could be introduced in minimally invasive surgery, with the aim of improving the safety and accuracy of surgical procedure by providing the ability to perform intraoperative, dynamic, and morphofunctional studies. Indocyanine green is a tricarbocyanine dye having a molecular weight of 751.4 Dalton. It is a negatively charged ion that belongs to the large family of cyanine dyes. Dry ICG is stable at room temperature. This is also the form of pharmaceutically available ICG. ICG is soluble in water but is not readily soluble in saline. In aqueous solution, ICG molecules tend to aggregate, which influence their optical properties. The aggregation depends on concentration and time. The spectral stabilization is faster when ICG is dissolved in distilled water. ICG works in the so-called tissue optical window, that is, the near-infrared light used both in excitation and fluorescence, penetrates tissue several millimeters or even further. The peak optical absorption wavelength of ICG is approximately 800 nanometers, with a fluorescence wavelength of approximately 800 nanometers in water and 840 nanometers in the blood. These wavelengths cannot be observed by the naked eye, while the use of video camera with high sensitivity in the near-infrared wavelength is used for measuring ICG fluorescence. The use of optical technology in the near-infrared wavelength for tissue measurement of ICG is advantageous as it can avoid the influence of autofluorescence and allow measurement of relatively deep tissue. The limitation of deep observation in human tissue is strongly related to the wavelength. For tissue measurement, hemoglobin and water are the main absorbance molecules. Hemoglobin strongly absorbs light at wavelengths shorter than 650 nanometers, while water absorbs light at a wavelength longer than 900 nanometers. The wavelength between 605 and 900 nanometers, termed the optical window, has high transparency because of low light absorbance by hemoglobin and water. The peak excitation and emission wavelengths of ICG are height 900 nanometers and height 104 nanometers in the blood and the water respectively, which are both within the optical windows. Thus, the ICG fluorescence method can be used to provide angiographic assessment of blood vessels or lymphatic vessels located relatively deep, up to 10-12 nanometers in tissue. With respect to image quality for tissue measurement, it is necessary to consider both light absorption and scattering. In particular, adipose tissue has low optical absorption but very high scattering characteristics, which result in blurring of the fluorescent image. For the reason, parenchymal, lymphatic, and mucosal tissue are the best target for clinical fluorescence use. Nowadays, ICG fluorescent guide surgery has a worldwide diffusion. It's actually employed for several different applications approved by the FDA, as the study of biliary anatomy, the lymphatic mapping, the evaluation of parenchymal perfusion and blood supply to bowel and mucous flap, the study of anastomotic perfusion, and the identification of liver metastases. Despite the popularity of this technology, some issues must be yet properly defined, as the ICG administration dose for each kind of procedure, the correct timing for fluorescence detection, the quantitative analysis of fluorescence peak, and the clinical applicability of the tailored target fluorescence in the field of surgical oncology by the conjugation of ICG with monoclonal antibodies direct against tumor antigens. The scientific community is actually on work to answer to this issue, and a more recent literature in the field of ICG-guided surgery has proposed important innovation at the beginning of phase 3 studies.